Thank you. So we come to the last talk of the workshop, which will be given by Natarajan Shankar, who is a distinguished senior scientist in the computer science laboratory at SRI International. And you can see the title of his talk, Beyond QED, AI, Theorem Proving, and the Quest for Beautiful Proofs. Please.
Well, it's a pleasure to be participating in this very interesting meeting. Thank you to Mohammed and Gehan for organizing this and for the kind invitation. So some of the points I'll be making probably overlap quite a bit with those of others who've presented talks. The hope is that I will have some new perspective on this and maybe spark some discussion. The points here are actually meant to be provocative. I think we are at a crossroads at this point with the power that is being exhibited by AI technology, and we have some interesting choices to make. So I think it'll be nice to have this discussion perhaps going on in these next few weeks and months to exactly figure out what the path ahead is going to be. So AI has been around a long time. In fact, the person I did my postdoc with, John McCarthy, is the gentleman who coined the phrase artificial intelligence. SRI has had an AI lab, AI center for a very long time now. I think it's been more than 60 plus years. And there have been many significant advances over these basically 70 years since the Dartmouth conference. Now, the AI techniques can be classified as algorithmic, symbolic, and statistical. So algorithmic, for instance, could be something like a search algorithm and so on. Many deductive procedures are also algorithmic, but they are typically symbolic. That is, you work with a symbolic representation and you manipulate that in order to achieve intelligent outcomes. And more recently, we've seen the explosive growth in statistical AI, specifically generative AI. Now, these things have been studied for a long time, and people have been looking at various ways of combining these to maybe reach better outcomes. But at this point, it looks like statistical AI is the kind of dominant paradigm here. So this actually opens up opportunities for the other approaches, for both algorithmic AI and for symbolic AI. It really does open up a bunch of synergies, and I will talk about some of these as we go along. So the question here is really, how can we leverage the explosive abilities that we're seeing in generative AI to be more effective at creating mathematics, at understanding mathematics, at applying mathematics. And in particular, a lot of this will hinge on the ability to create beautiful mathematics, to create beautiful formalizations, and essentially leverage the structural beauty of the mathematics that we're creating in order to make it more applicable, more extensible, and so on. By the way, you can interrupt me anytime for questions. I'm happy to field questions at any point in the presentation if you want to stop me. So the kind of notion that mathematics is beautiful has been around for a while, and what beauty actually delivers in mathematics is that some conclusion is actually inevitable. We understand more about it because of the beautiful way in which the argument is actually laid out for us, the beautiful way in which the mathematics itself has been abstracted, and this structural beauty also makes it more broadly usable. That is, these results are not only extensible, they are more applicable to more things in our daily lives, and we can extract actionable content out of things that are beautiful. So in terms of whether we do care about beauty in mathematics, we do care. It's not just enough to say that a theorem holds. It's really something where you want to say the proof of it has a lot of content in it that you can mine for value. In many cases, actually, many of my points are nuanced. They're not black and white. In many cases, it's actually a big deal to know that something is indeed a theorem. So, if we can settle the Riemann hypothesis, that is a big deal. We can care about the beauty of the proof later on. And the thing that we do in mathematics is essentially refine the proofs to a point where we make them more and more beautiful so that it's understandable by many more people. Things that at one point were open problems or really pieces of complex mathematics that were only understood by a few people become accessible to the vast majority of us through this process of essentially polishing the arguments to make them more and more beautiful. And in particular, one of the things that formalization does for you is because of the need to actually explain the mathematics to a machine, you tend to inherently favor beautiful arguments while you're doing it. So that's something that if you don't do that, there is a kind of heavy price to be paid for the ugliness in the mathematics, and this can actually make the development of formal mathematics exponentially more difficult. It also builds up technical debt. You don't get as much value out of the formalizations that you've done. And so it is really important to pay attention to this. So I actually disagree with this quote here that Donald Knuth has, science is what we understand well enough to explain to a computer. That's great. I think I get that. But there is also art to doing formalization that is quite critical to the effectiveness of the formalization itself. In fact, I had De Bruyne visiting the Bay Area once, and Knuth was introducing him for a seminar. And the way Knuth introduced him, he said, every once in a while I ran into a problem that I couldn't solve, no matter how hard I tried. I would send this problem by mail to De Bruyne. And by return mail, De Bruyne would send me not only the solution to my problem, but a technique that would work for my next 50 problems. So this is really the kind of thing that we want to achieve. We want to have a kind of De Bruyne on every desk. Now, the other thing that you have with formalization is, in many cases, we think, oh, we've reduced it to something that is machine checkable, so our work is done. And the feasibility of this was actually established in the early part of the 20th century. The idea that a large portion of mathematics was formalizable, and in some sense, this could be reduced to a few mechanical rules, was already established in the early part of the 20th century. But the ability to actually do this beautifully means that you're in some sense creating an architecture. You're not just creating a building that's functional. You're actually creating a beautiful architecture that has aesthetic value as well as the correctness. Now, the question of understanding is a complicated one. It's not clear that just because something is beautiful that it's more understandable. It tends to be. But the thing about mathematics is that, as von Neumann says, you have to get used to it. And part of the beauty that you have in this, I'll show you some examples, is that it makes it easy to get used to doing the mathematics. Again, a lot of us are engaged in this pursuit because we believe mathematics is inherently beautiful. I spend a lot of effort polishing proofs because I believe that there is this proof from the book out there. And if we could only work hard enough to seek it out, we will find it. So this is something that I think drives a lot of us. But I kind of take exception to some of the concepts of beauty that mathematicians actually that tends to appeal to mathematicians. In particular, I find a lot of proofs that mathematicians present as beautiful to be kind of sleight of hand exercises. They hide the complexity somewhere, and it only kind of bites you when you try to formalize it. As an example, I use Dijkstra's proof of the pigeonhole principle. Here, you want to show that there's no way to assign n plus 1 pigeons to n holes without actually making one hole contain 2 pigeons. And the argument is very straightforward. It's basically the idea that the maximum is at least the average, and the average number of pigeons per hole is greater than 1, and the maximum has to be a whole number, so it has to be at least 2. The difficulty with this argument, as beautiful as it appears, is that it introduces a number of concepts that you really don't need for just the basic pigeonhole principle. The counting, the maximum, average, all these operations are implicitly introduced, and because you're familiar with them, you think this proof is beautiful. Actually, this proof is beautiful from another respect. It's not great for the basic pigeonhole principle, but if you want a more generalized version of it, then this is a kind of argument that you may want to actually exploit. And so the important thing here is that our work is not done when we reach QED. We still need to explore many variations of the proof, many ways of presenting the mathematics, many ways of refactoring it to a point where it then becomes something that is a beautiful formalization. So a little bit of personal history out here. So my own work on this started in early 1982. That's more than, I think, 44 years ago. So the project I was engaged in was formalizing Gödel's incompleteness theorem. Now, this, just because a thing has it's called a theorem doesn't mean it is the same thing to all people. There are more difficult ways of proving this theorem, and there are easier ways of proving this theorem. In particular, if you have a formalism where computation is given to you, then it's easy to formalize this theorem. So the task was actually very well specified. It was to prove it in a theory that would be acceptable for practical mathematics, but also did not build in computation. So it was essentially specified as a fairly challenging exercise. And this was, there were a few formalizations before this. There's a couple that I can mention, namely Van Bentham-Gitting's formalization of Landau's foundations of mathematics, and the Bledsoe's formalization of Morse's set theory. But when you look at those, there is actually no complexity to those formalizations. Those exercises are actually fairly modest exercises. So this was really the first big formalization that was attempted. And at that point, the theorem proving technology I used was a theorem prover called Thumb, which was actually developed mostly at SRI. By the way, it's an outstanding system. It's easily, even in all the years that have passed, this is, I think, the pinnacle of theorem proving. I think Thumb was the pinnacle of theorem proving. And so but at this point, because this was a pretty large exercise, failure was indeed an option. And so the kind of imperative here was to actually build a beautiful formalization. Without this, the exercise would have failed. And in some sense, the credit here doesn't belong to me as having done this. It really does belong to the theorem prover for having forced this kind of beauty on the formalization. That is to make it so that it actually is something that if you do it beautifully, it'll work. So that's the lesson out here. And if you haven't read the book Metamathematics Machines and Gödel's Proof, I urge you to read it. There's quite a lot of content here. Many of the things we're saying in this workshop actually have been covered in that book, so you can go read about this exercise and also some of the lessons drawn from it, which are still, I think, relevant today. The proof also contains some hidden delights. So if you read it, you'll find there's actually quite a lot of useful content, including the verification of a SAT solver with proof objects that turned out to be quite crucial to the proof. This actual SAT solver made it possible to mechanize proofs in the object theory using the meta theory's mechanical power. and this made the proofs actually fly. So even by modern standards, this is an extremely well mechanized proof, especially by modern standards, I should say. So in 1984, I had the privilege of visiting Mike Gordon and Larry Paulson at Cambridge. And in fact, Larry was at that point still working on a system called Cambridge LCF and was just starting to think about Isabelle at that point. So it was actually a very interesting time to be there. And since I didn't have my files with me and I couldn't work on the incompleteness theorem, I started working on the Church-Rosser proof. And one of the things that the reason I started looking at that is that Boyer had attended a meeting in 1983 on Lisp and functional programming. It was a historic meeting because it was actually attended by Kleene, Rosser, and Curry. And they were quite astonished to see that their work was finding a home within computer science and was so highly regarded. And at that meeting, actually, Boyer got into an argument with Alan Perlis of DeMilo, Lipton, and Perlis, Social Processes and Proofs. And the moderator of that debate actually suggested looking at the Church-Rosser theorem proof because it had kind of a checkered history. There'd been many attempts and many failures and proofs that were 600 pages long and so on. So I did, because I was at a loose end at Cambridge, I did try it. And it turned out to be quite difficult. I was not able to get an argument to go through. And Boyer actually repeatedly suggested looking at the De Bruyne representation. And at that point, I actually did not know what the representation was. I did not think that just a mere change of representation could have any impact on the ease or difficulty of the proof. But boy, was I wrong. So once I actually had Boyer explain to me what the De Bruyne representation was, it only took me a single night to finish this proof, the proof of this diamond property of this little diamond here. And the rest is just a couple of inductions to get the full Church-Rosser proof. So this, again, the kind of battles with the theorem prover do lead you to value elegance and beauty in getting proofs done. And again, remember, these are things that, they were done essentially beautifully the first time they were formalized. There was no revision or anything like that. The theorem prover actually leads you to things that are beautiful in a kind of very, very organic way. Okay, so by say 1985, the picture was pretty clear. The claims that DeMilo, Lipton, and Perlis had made about how if mathematics was a mere matter of logical progression, we would still be counting on our fingers, was not the case. There were, in addition to my own work, there were several other examples that showed that large-scale formalization was no longer a major challenge. And what that means is that your worry is not about getting to QED. You will get to QED by hook or crook. What you need is actually to be paying attention to the value of the proof that you're building in the process of getting to QED, so that you make sure that it has intrinsic value, the clarity, insight, the ease of mechanization, and so on, and extrinsic value as well. That is, the fact that it's beautiful means that all of the results along the way are reusable, the techniques are reusable, and in addition to the final result on which you proclaim QED. And so in 1988, Bauweiss started this computers and mathematics column in the notices of the AMS, and he invited me to write the first column. So this is a quote from that column: of all the sciences, mathematics is the one that has relied least on technology. Generations of mathematicians have practiced their art and communicated their ideas with only the simplest writing implements. The traditional mathematician perhaps views computer proof checkers to be unnecessary diversions that are unlikely to have any significant positive impact on the field. I would like to suggest that proof checkers can have a useful role to play in mathematical practice. So we are still not there. It's not routinely used in mathematical practice, but it's really interesting to see the progress that's happened, particularly since the 2017 big proof to now. It's really interesting to see how much traction formalization and computer-assisted proof checking has had, thanks especially to Leo's work on Lean and actually many others. So any questions at this point? Okay.
I think that most people are not actually able to ask, to speak, right, because of this setup. I mean, I can only speak because I was another presenter.
Okay, Kevin, you can ask a question if you have one.
No, I'm just enjoying the show. I'm not asking. I'm just pointing out that most people are not able to ask a question.
There must be some way of posting it in the chat, right?
There is one question in the chat. So what is the title of the recommended book again?
I think it's called Metamathematics, Machines, and Gödel's Proof.
Okay, thanks. Yeah, go ahead. Just go ahead.
Okay, yeah. So what I then saw, actually, then I started, after I finished my postdoc with McCarthy, I started working at SRI. And at Stanford, there was a higher order logic theorem prover called EKL. And at SRI, there was another higher order logic theorem prover called EHTM. And EHTM was interesting. It had an interesting combination of higher order logic and SMT solving. SMT solving had been invented in the 1970s by Shostak and Nelson and Oppen, Shostak at SRI and Nelson and Oppen at Stanford. And this was the only engine. And with all of these systems, the pain was in debugging. That is, by and large, you were dealing with definitions that were incorrect, theorems that were slightly off, proofs that were kind of misguided. And so 95% of your time is spent debugging. It's only 5% where you actually hit QED. And so these systems weren't optimized for this QED case, and they weren't all that useful. The other systems that were around were extremely manual. So the halls and the kind of LCF style systems were extremely manual. And as is always the case, the happy optimum is somewhere in the middle. And this is what I decided to focus on. The other thing that was the case here is that they were just using logic in a kind of vanilla form. They were not putting in the features that actually made logic a little more interesting for representing mathematics, for discovering proofs, and so on. So in linguistics, this is often referred to as a Sapir-Whorf hypothesis, that language influences thought. And it's generally regarded as fallacious, but it's true in a few cases that language does influence thought. But in formal languages, it plays a huge role. So in formal languages, language actually heavily influences thought. There are many, many examples of this, but I'll use Tony Ho's invention of the recursive quicksort as being inspired by recursion, the availability of recursion in Algol 60. So this is something that I think you see all the time in formalization. There are many features in the language that force you to think about the proof in a certain direction, or force you to discover proofs that have a certain shape to them. And so I started working on PVS to explicitly capture this, both the kind of ability to express things nicely as well as to be able to debug more productively. So, and the point of PVS was really to build beautiful formalizations using this combination of language and mechanization and the synergy between them. So, the name PVS stands for Prototype Verification System. It's really been a prototype. It's been a medium for exploring a number of ideas. Many of these ideas are ones that you actually probably use today, but they were initially prototyped in PVS. So it's been quite effective as this kind of prototyping, research prototyping medium, and for essentially building beautiful formalizations of mathematics and computing. So in introducing PVS, this is the kind of motivational paragraph that we wrote in 1992, that the design choices were really focusing on the scalable construction of robust proofs. Our experience with mechanical verification of complex designs and algorithms has led us to conclude that just as with software, there's a life cycle to a mechanically checked proof. In the initial exploratory phase of proof development, we're mainly interested in debugging the specification and putative theorems and in testing and revising the key high-level ideas in the proof. An important requirement in this phase is early and useful feedback when a purported theorem is in fact false. Once the basic intuitions have been acquired and formalization is stable, the proof checking enters a development phase where we take care of the details and construct the proof in larger leaps. Efficiency of proof development is a key requirement here. In the third presentation phase, the proof is honed and polished for presentation in order to be scrutinized by the social process. Readability and intellectual perspicuity of the proof output is the goal here. The final phase is generalization, where we carefully analyze the finished proof and weaken and generalize the assumptions, extract the key insights and proof techniques, and make it easier to carry out subsequent verifications of a similar nature. Maintenance is a special application of generalization, where we adapt a verification to slightly change assumptions or requirements. Robustness of the proof procedure is a useful attribute here. And I can say that by and large, things have lived up to this kind of manifesto out here. So let me give you kind of one example of this. This is Cantor-Schroeder-Bernstein. PVS has had a Cantor-Schroeder-Bernstein in it from like the very early 90s. This was one of the first proofs that was done. But I wanted to kind of explore a proof that used the Knaster-Tarski theorem directly, that often the proof just kind of embeds this reasoning inside it for as a special case of Tarski-Knaster. But I wanted to explore this. And I only had a vague recollection of what the proof looked like. And so in kind of one setting, I was able to interact with the theorem prover and come up with this proof. Just from a vague recollection. And this is actually the way I use a proof assistant. I've stopped using paper, actually. I just kind of start to explore my thoughts at the proof assistant. So let me just go to the PVS window and show you the thing here. So So this is kind of what I started writing. So I have the CSB of two types. I'm trying to show that if there's an injection between A and B and one between B and A, there is a bijection back and forth. And this is roughly the argument as it's written in the other case. And this was my first attempt. And if you look at the kind of proof out here, so I will step through it. So if you look at the proof out here, it's extremely manual, but it has a few kind of rabbits in it. The first thing I do is I remove the universal quantifiers. I spread things across the sequent arrow. The next thing is I bring in the Tarski-Knaster theorem that I want to use. So that's that. Then I instantiate it with the predicate. So these are all the rabbits. These are the things I knew from before. And now I have this idea that if I take the complement of the image, whoops, sorry about that. My work has these annoying things which starts to interfere with. Okay, so if you bring in these kind of things, the instantiated, then you go through this step called ground, which is essentially, doing SMT solving, say. And each proof goal actually has an SMT state associated with it so that you can simplify things relative to that. And this takes out a lot of tedium from the proofs, just having that ability there. And it turns out Shostak designed his procedure quite nicely to address this particular case of multiple proof goals. And so you can kind of clean things up a bit and so on. And so you can go through this proof. It's the first attempt. And this is, again, the first attempt succeeded in this case. So here, because I'm kind of feeling my way around, there were many back and forths. I was actually trying things out, going back and forth. But in the end, just within one session, I was able to finish the proof. So So then I go back here, and actually this was a difficult exercise. I was trying to clean it up and break it down into lemmas and finally prove the CSB2, the same theorem, but with a nicer proof. And so all of these now have very short proofs. So if you look at any one of these, then you'll see that it just has like 4 steps in it. You can just kind of step through it. Okay, so by the way, the reason I'm using Emacs is that I'm a developer, and I tend to actually have more keystrokes available to me through Emacs than through the VS Code interface. So that's the reason. It also helps me show you a few things. But if you look at this, if you say show proofs theory, you can see all the proofs, and so it's showing you this long proof, and then all the other proofs are actually fairly simple. Okay, so and this is indeed, in my opinion, quite a beautiful proof. Okay, so let me go back to the talk. And it's why it's well worth spending all that effort to actually come up with something that's beautiful. By the way, you can compare my proof to those that others have done with other systems, and you can judge for yourself what you think of it. Okay, a second example here is actually a problem that was posed by me in a verified software competition. And Rustin Leno came to me and said, hey, that problem he thought was too challenging for the competition, that I shouldn't have included it. And he said, why don't you do it yourself? And so I did try it one morning when I had some time to spare. And so you can, I'll walk you through the steps that were in there to show you how, the elegance of the formalization actually helped the thing a lot, and what would otherwise be a tricky problem. So you want to do n queens for any n. So you have a theory with parameter natural numbers. The board is just an n element array. So arrays are just from below n to below n. So that is 0 dot dot n minus 1 to 0 dot dot n minus 1. And this basically says that two boards, A and Queen, agree on all the values on rows from 0 to I minus 1. So the idea is that the Queen positions for those are the same. Okay. And now here comes one of the key steps that I took in this, which is that I know that the search can fail. I mean, many search problems can fail. So the idea is that normally you represent that kind of failure with what's called an option type. And in this case, we call it a lifted type. And if the lifting returns bottom, it has some meaning. And if it returns a value, that has some meaning. The problem is that we don't really spend time thinking about that meaning. So here, the QLift predicate actually takes another predicate as argument. And it essentially says that when you return, you give it a lifted board. So if you return bottom, it means there's no solution. There's nothing satisfying P. If you return up of Queen, then that particular thing is a solution to the search problem. So it does satisfy P. And so a good extension, B is a good extension of board A from I onwards if it extends B from position I and satisfies P. So that's the idea of B being a good extension of A. So then the search is actually factored into two subproblems. One is, for a given row, finding a position for a queen in row I, so finding position J for queen in row I, such that that can be extended to a good solution, and then scanning the rows. So this search is is looking at row I, and it's looking at partial board A. It's looking to satisfy the predicate P, which eventually will be the good queen's predicate, but it's left open as a variable now. And it's looking at a queen position J for the column, such that every attempt for something below J has failed. So you were not able to find a good extension for it. So that's one of the tricks out there is that you want to keep track of the partial work that you've done in the subtype. The last argument here is actually also very interesting. It's a continuation argument. It says basically, that you have an operation that can take a board and give you a good extension of it. And it can give you a search that can either return failure, which means there's no good extension, or it can succeed and with a good extension. So that is a continuation argument. And with that, you basically say that if you've hit the limit on the number of columns, you return bottom, you fail to position a queen in that column, given the preceding work that you've done. So you propagate that failure back. Otherwise, you position the ith queen at position J and continue the search with F. If that returns bottom, you continue the search with J plus 1. If that returns a solution, you pass that solution back. Okay, that's the idea, and it terminates because J eventually reaches N. And the other thing is that you scan the rows. That's the big operation here. So you're going to go from rows 0 through N and try to find a queen satisfying position P. So if I is equal to N, then if P of queen holds, then, essentially if I is equal to N, then you've positioned all the queens. You just have to run the predicate on it. If that succeeds, then you return up of queen. It'll satisfy this Q lift operation here. Otherwise, you return bottom, and it means there's no solution that extends that. It satisfies that. And if not, if I is not equal to N, then you continue the search. That is, with I essentially scanning I plus 1. Okay, that's the intent out here. So you go on to the search with I plus 1 out here. I'm sorry, you call the search procedure on I, but with the continuation of scan of I plus 1. So this becomes a continuation to the search. Okay, so the nice thing about this is, again, you would normally do this with mutual recursion, but the continuation actually takes care of mutual recursion. All of the proof obligations are local. That is, you've positioned every little check at the precise point at which you can ensure that it holds and where it's useful for the rest of the procedure. And then finally, what you do is you say the find board is just scanned from 0 with the where all the queens are in position 0 for all the rows, and then you start working from that. And then you give it the good queen predicate of how queens should not be placed, and then the whole procedure of n queens is just find board of good queen. That's the whole thing. And then you can run it on n, from 0 to n and so on. So this generates 21 proof obligations, and only a handful of these actually require any interaction at all. And so the whole proof took about 45 minutes. And I can show it to you, but I think you may get the idea that this is actually quite easy. Any questions at this point? Okay, so this is, as I said, there are many kind of tricks in this formalization that was done in 45 minutes that made it possible. But these tricks are universally useful. They are things that tell you, how to handle certain kinds of mutual recursion, what the option type really means. If you may have used it thousands of times, but you may have never reflected on what its property is. The language forced you to think of these things. It forced you to think about what is it that the continuation is doing? How do I specify that I've partially solved the problem that I'm trying to continue a partially solved problem? All of these things are actually forced on you by the language, and it gives you a really elegant proof. And this is the way things are done over and over and over again. I mean, this is kind of a very natural style of doing these proofs, simply because you have this combination of the dependent predicate subtyping and SMT solving combining together to work with it. And so in many of these cases, grind takes care of the tedious stuff quite easily. And all of these procedures are actually, grind is also it's not an endgame prover. Someone asked about sledgehammer. It's not like sledgehammer. It's not an endgame prover. It actually simplifies things and gives you sub goals that you can look at in order to see why it failed. So you can also run grind in a kind of glass box mode to see what it did internally. So you can look at its internal behavior and see what it may need to actually proceed with the proof. And so a lot of it is actually there to give you a lot of useful information to do proofs productively, to do beautiful proofs. So these are things that AI might eventually learn. I don't know, but when I ask it to explain, when I ask Claude to explain, what's going on with this, it's with a slight variant, actually, a more efficient version of nQueens. It basically gave me a vanilla description. This is pretty good. It really did understand what was going on out there about continuing the search, the success and failure, and so on. But it's not great. It missed the kind of whole point of why this exercise was, what are the kind of critical elements of this exercise that make it beautiful and useful. And a human being would have, in particular, an expert human being would have grasped those points immediately, whereas the AI is not able to. And we actually tried this again yesterday. And again, the results were even more disappointing than this. This was actually a better response than we got with Claude yesterday. So, the key point here is that there is a lot of really interesting progress in the generative AI. We find, for example, the agentic use of AI, these models are able to generate excellent PVS. They're able to actually generate idiomatic PVS. They're able to actually make use of the way I have used some of these idioms. They're actually able to make use of them without any real prompting, just by going through the agentic loop. The ability to actually give informal proofs, formalize these proofs, do them in idiomatic form, explain counterexamples to you, is really a kind of it's not only a tribute to the amount of human creative input that has gone into training these models. We can pat ourselves on the back for having created all this knowledge that has gone into training it, but their own inherent ability to actually crystallize that data into something that is useful and insightful. I'm not a Luddite or anything like that. This is technology that I think is useful as long as you use it with this focus on tasteful, insightful, understandable, maintainable content. So in particular, I think that, with respect to those 4 phases of proof development that I mentioned earlier, the generative AI can definitely help with the exploration phase. It can help you take informal formalizations and formalize them. It can explain things to you. It can explain failures to you, give you alternative suggestions of ways to formalize things and so on, so that it can help you make good use of the target language and with idioms that perhaps you weren't aware of. So it helps both novices to navigate systems that they're not that familiar with, but it also helps experts deal with complexity to be able to actually take advantage of the capabilities that these models have to allow you to progress in big leaps. So experts too can benefit from this. In terms of the development phase, you can have proof recommender systems that help you guide proof construction. They can help retrieve lemmas, tell you whether you're making progress or not, tell you why you might be failing along a certain path in the proof. So we've built systems like this in the past. We've built auto formalization like about 10, 12 years ago. But most of these things are actually being subsumed by modern generative AI and many of the coding tools that are available. One phase that can definitely help you with this in presentation, you can actually send it through these agentic loops where you want it to clean up your formalization and make it a lot more explainable, make it something that has been very well documented, and it's not only capable of being published, but it helps you come back and revise the proof in conjunction with an AI agent, perhaps. And in terms of maintenance as well, you can put it through agentic loops where the proofs are refactored. You're able to essentially organize things so that the if you build a library out of it, the library is fairly self-contained. You don't have to, you're not missing content in these libraries, and you have essentially a notion of an API that is sensible for these libraries. So where does this leave us in the second quarter of 2026? So already in 1999, Tim Gowers has this paper, Rough Structure and Classification, which contains this amazing dialogue between a mathematician and a putative AI agent. You need to read the paper to actually just digest that dialogue. And it follows with this depressing conclusion. I expect computers to be better at proving theorems than humans in 2099. I do not feel happy about this, but I expect the impact on my own mathematical life to be entirely positive, because a semi-intelligent database of the kind I've described would be a wonderful resource and would take a great deal of drudgery out of research. There might even be a golden age where computers are good at exercises, but not good at having deep insights. Then, instead of wasting a week not noticing that a hopeful lemma had a simple counterexample, one could get the computer to check it. However, such a golden age, if it occurs, is unlikely to last for long. The work of the mathematician would be simply to learn how to use theorem-proving machines effectively and to find interesting applications for them. This would be a valuable skill, but hardly the pure mathematics as we know it today. By the way, Thurston also has a similar paper, I think around 2001, where he also tries to position what the role of mathematicians would be if a lot of mathematical content development was automated in this way. And part of this argument he makes is that a lot of what we do as mathematicians is increase human understanding. And this is still the work that we need to be doing with or without automation. So we might already be in Gauss's golden age. As I said, these AI models are getting pretty good at things that we want them to do. You can give them textbook chapters, they formalize them quite nicely. They do well in math competitions. They are beginning to solve non-trivial open problems. You can also use them to scale up formalizations, and that's an important role that they will have. But again, we reach this crossroads. So will they amplify human intelligence or dumb us down so that we are just sitting there examining and trying to digest the output of these inanimate models? Will they eventually just replace us and turn us into a kind of feudal society? Will they even need proof assistance for ground truth? If they get good enough, they can build their own kernels and do their own checking. They can take care of this themselves. They don't need to use our carefully crafted proof assistance. The bigger question here is really kind of a societal impact. Are we really on the verge of realizing Leibniz's dream that we can resolve disputes by collectively acknowledging ground truths? Or is it going the other way? Are we just kind of retiring into our epistemic bubbles and slowly kind of untethering ourselves from reality, generating content that nobody cares for, and doing it simply because it can be done? So Leibniz, when he thought about symbolic logic, his hope was that humanity would have a new kind of instrument, increasing the powers of reason far more than any optical instrument has ever aided the power of vision. So, can we use this technology in a judicious way? Since it's been built on our output, this is something that, we provided the training data for this. Can we use it to actually expand humanity's power of reason, to do better science, to do better philosophy, to resolve disputes of every kind, at a societal scale? So the conclusions, more specific to our enterprises that, QED is not really the end goal. The goal is to really go beyond QED to create these beautiful artifacts, proofs, tools, libraries that really amplify human ability, allow us to take on big challenges, to design better software, to design better systems, better hardware, to build computer security and trust into all of these artifacts that we rely on so heavily. So if we delegate all of these interesting tasks to AI, the real danger, there are actually many significant dangers, but the key ones are we will be building up technical debt. We will be essentially freezing tools at a level that is only going to create more problems for us down the road when stuff explodes on us. And we're going to be de-skilling human talent. Humans are going to be doing the dumb work and delegating the interesting stuff to AI. This will mean that a few people will be owning the means of production of content. And the reason AI companies are valued as high as they are is that the assumption is that they can essentially replace intelligent human input with these machines, and that will give them enormous leverage. And so this would accelerate inequality and have us all drowning in a AI slop, which we kind of already are to some extent. So we need to fight this battle. I think this is something that has to be actively fought. We need to make sure that there are standards to how we create human knowledge, how we share it, how we make these tools themselves available and useful to others in some dramatically important ways. And if we do this, what we will have is, I think, a better way of creating the engines of human progress. And some of this will be that it'll help many more of us, machines and humans, get used to mathematics. Thank you.
Thank you very much for this very interesting talk, and especially for putting into context the topic of the workshop. So let's take a few questions. There are a couple of questions. So the first one, I have a question about the conception of beauty or elegance, and what you think about their opposites, ugliness and inelegance. Do you think there might be some intrinsically ugly or intrinsically inelegant proof, or perhaps intrinsically ugly theorems which only have ugly proofs? Are there any proofs, theorem that you currently think are hopelessly inelegant?
Yeah, so great question. So this is the kind of notion of beauty, I think, again, is a very subjective one. And as I mentioned with that Dijkstra example, that proof is ugly from one perspective, that it depends on more than it needs, but it's beautiful from another perspective in that it gives you more content from its proof than you would get from the basic one. So it's kind of beauty is still in the eye of the beholder. Part of what drives me in terms of this is that, I'm sure there are theorems that are inherently ugly. There are proofs that are inherently, and there are theorems that require proofs that are inherently ugly. That's certainly going to be the case. I think an information theoretic argument will establish that there are many theorems and only a few beautiful proofs. But the thing that drives me, at least, when I'm thinking about something, is that I will keep things kind of boiling. I'll keep the pot boiling just to make sure that I have left no stone unturned in terms of finding a beautiful proof. This is something that for me is really a driving thing. Just like for Hilbert, we must know, we will know. for me, we will know is not enough. I need to, I need to know the beautiful reason why. So that I think is the driving thing. Now, the other thing about this is that my own sense of what is beautiful is not necessarily the kind of mathematical elegance. There are many things that mathematicians do that are kind of coded. I find it amusing that proofs by induction. Mathematicians seem to not say the word induction. It somehow is embarrassing to them that something was, and so the typical presentation that you get, they tend to contain many more rabbits than they need to. So for me, the beauty is really that if you can reduce it to something that is minimizing the rabbits, and after, once you've introduced these rabbits, once you tell me how to do the induction, the base case and the induction steps just drop out automatically. So I have actually many examples of this, and these are things where for me, it's a kind of crystalline mechanical beauty that I appreciate. So even though some of the mechanization in that may be complex, it doesn't matter, because these machines, once you've reduced the problem to something that they can handle, you don't need to think about it anymore. So that's also important. I mean, that's the virtue of grind, is that once you've kind of got things that look obvious, then grind takes care of it.
Thank you. So another question. So what is the title of this 1992 QED paper?
Oh, I don't remember, but it's kind of a system description for PVS.
There's in the comments, there's a link to it, a prototype verification system.
I think that's its title. Yeah, I think it's a prototype
So
verification system. Yeah.
Okay, thank you.
Yeah, it's actually a short paper. I think it's like about 4 or 5 pages.
Thank you.
It's,
so another
it's
question.
6 pages, and it's been posted in the chat.
Yeah.
Okay. So the next question, one of the justifications that people often give for using category theory is that it provides a general language in which features common to different areas of mathematics, including constructions and proofs, can be more easily recognized. Do you have any hope of a similar common ground for automation?
Yeah, absolutely. Yeah, that's entirely correct. Yeah, you can have runaway abstraction. At some point, you can take abstraction to a point where it really isn't giving you mathematical insights. But the idea that you can have representations that offer not only kind of more general theorems, but more systematic proofs is really the point that we should be striving for here.
Okay, thank you. So we will have plenty of time for discussion, I guess. So we will resume the discussion in 15 minutes, 16 minutes roughly. So also a short message for the previous speakers from previous days. So you are welcome to attend the next panel session in case there are questions which are directed to you. Thank you. So let's resume in 15 minutes. Thanks, Shankar. Thanks again.